This is a demonstration of plot windows, a package of functions for drawing scatter plots, histograms, and other statistical graphs. Plot windows is written in Lisp and runs on a symbolic 3600 Lisp workstation. The user interacts with the system through a keyboard and a 3-button mouse. Plot windows follows the desktop paradigm, invented at the Xerox Palo Alto Research Center and popularized in the Macintosh personal computer. The screen is divided into several windows. I will illustrate some of the capabilities of plot windows by looking at a few data sets. The first data set was collected by Francine van der Walle of Princeton University to study the demographic transition occurring when Switzerland changed from a medieval agricultural society to a modern industrial society. It consists of the values of 6 demographic variables for 47 Swiss counties in the year 1888. The variables are proportion of population with education beyond primary school, proportion of Catholics, infant mortality, fertility, proportion of inhabitants engaged in agriculture, and proportion of draftees receiving the highest mark in the army examination. The main difference between plot windows and plots in most other statistical packages is that plot windows are persistent objects. They do not go away as new commands are typed and the screen scrolls. Producing a plot is like putting a sheet of paper on a desk. We can perform the same operations on windows or virtual sheets of paper that we are used to from handling real paper, plus some more. The plot in the upper right-hand corner of the screen is a scatter plot of education versus Catholics. Note that it consists of 3 panes: the title pane on top, the graphics pane containing the actual graph, and the menu pane on the bottom. Let's move the plot to another place to make it bigger. A plot can be moved by pointing at the double arrow in the title pane and clicking left. An outline of the window will follow the mouse. Clicking left again deposits the window at the new location. A plot can be reshaped by pointing at one of the arrow icons in the title pane and clicking left. The corner will follow the mouse. Clicking left again deposits the corner in the new location. Note that the plot has automatically rescaled itself to fill the available space. Plots support a number of interactive operations. By clicking right on the title of a window, we expose a menu of possible actions. Selecting the menu item axis, for example, adds coordinate axis to the scatter plot. The plot reveals that there are essentially 3 groups of counties: Catholic counties, which are low in the education variable, Protestant counties, which are also mostly low, and 3 counties which are about half Catholic and have an above-average fraction of educated inhabitants. It is reasonable to conjecture that those are the urban counties. Let us now have a look at some of the other variables in the data set. Here is the Lisp expression we have to evaluate in order to draw a scatterplot of the variables farmers, fertility, and fit draftees. Plots by default appear in the upper right-hand corner of the screen. Percentage of farmers is drawn on the x-axis, fertility on the y-axis, and fit draftees on the z-axis, which we can't see because it sticks out of the screen. We now have on the screen a plot of Catholics versus education and a plot of farmers versus fertility. This by itself isn't any more useful than looking at the plots one after the other. We cannot reconstruct the 4-dimensional coordinates of the points from the 2 2-dimensional projections. For the reconstruction, we also need to know which point in one scatter plot corresponds to which point in the other. We need to be able to identify pairs of points representing the same observation. This connection can be established through painting and automatic updating. We select the painting operation in one of the scatter plots. Clicking on the paintbrush icon and moving the cursor into the graphics pane replaces the cursor by a little square, the paintbrush. Painting over observations with the left mouse button held down highlights the observations. Painting with the middle button down downlights. Let us highlight the cluster with the high proportion Catholics. Plot windows automatically enforces the constraint that the intensity with which an observation is drawn is always the same in all the plots showing the observation. Plots keep themselves up to date automatically. We see that counties with high proportion Catholic tend to have high percentage of farmers and high fertility. Let's put in a coordinate system. In order to perceive the three-dimensional structure of the point cloud, we have to spin it. Spinning is started by pointing at the leftmost icon in the menu pane and pressing a mouse button. Holding the middle button down makes the cloud spin around the screen y-axis. Releasing the button and pressing it again reverses the direction of rotation. Similarly, the left and right buttons control rotation around the screen X and Z axis. Rotating around the Z axis makes the points move in circles on the screen. We see that the Catholic counties also have a low percentage of fit draftees. Let us now reset the cloud to its original orientation. Next, we highlight the observations with low percentage Catholic. They tend to have lower percentage of farmers and lower fertility. Finally, let's highlight the 3 urban counties. They do not follow the pattern. They are about 50% Catholic but have the lowest values of fertility. Connecting multiple views of a dataset through highlighting and automatic updating was first suggested and implemented by John McDonald. It is a simple but far-reaching idea. Painting allows us to see associations between variables shown in different plots. Let us think for a second about what we are looking for when we paint. We highlight a subset of the observations in plot 1 and then look at plot 2. If the highlights in plot 2 are randomly distributed over all the observations in plot 2, we have not found anything. If, on the other hand, the distribution of highlights over observations in plot 2 appears non-uniform, we have detected an association between the variables in plot 1 and the variables in plot 2. Detecting non-uniformity and therefore association in our first example was very easy because the associations were so strong. This is not always the case. Let us look at a data set on survival of breast cancer patients. The covariates are age of patient, year of operation, and number of positive axillary nodes. The response is binary: 1 if the patient survived for more than 5 years, 0 if she didn't. Let us draw a scatter plot of number of axillary nodes versus age and a histogram of the response. The scatter plot shows age on the horizontal axis and number of positive axillary nodes on the vertical axis. To see whether there is a difference between the survivors and the non-survivors in those 2 variables, let us highlight one of the 2 groups by painting one of the histogram bars. I have highlighted the non-survivors. Look at the scatter plot. Can you see a structure? I am aware of the fact that you are handicapped because the quality of the video is so much poorer than the quality of the screen, But believe me, even on the screen it is by no means obvious what is going on. Highlighting the survivors is more suggestive. It appears that most of the highlights are on the bottom and the left of the plot. This is the corresponding odds plot. Pluses in the odds plot are drawn at locations where there are more highlighted observations than would be expected under random distribution of highlights over observations. Minuses indicate that there are fewer than expected under random distribution. We can also phrase this in probabilistic terms. A plus indicates that the conditional probability of being highlighted given position is higher than the unconditional probability of being highlighted. A minus indicates the reverse. In this graph, the conditional probabilities are estimated by binning the picture and counting highlights and total number of observations in each bin. The plus or minus icons are drawn in the centers of the bins. Bins with density below a threshold are discarded. It is not possible to estimate the probability of being highlighted given x for a value of x where there are no observations. The odds plot makes readily apparent what is going on. The survivors are overrepresented among the young patients and those with few axillary nodes. Let's highlight those that died. Obviously, they are underrepresented among the young and those with few axillary nodes. Using the inspector, we can actually see how many observations and how many highlights there are in each bin. We invoke the inspector by clicking on the pointed hand icon in the menu pane of the plot. Pointing at one of the icons and clicking left shows the values of several variables for the bin in the inspector window. This bin had 5 observations in it, all of which are highlighted. The expected number of highlighted observations under random distribution is about 1.3. The binomial tail probability is about 0.001. We will now change the odds plot to determine the sizes of the icons from the squared deviations between observed and expected number of highlights. Here is the statement we have to evaluate. Qualitatively, the picture is very similar. The difference is that the local density, i.e. the number of observations in the bin, enters in the calculation of the tail probabilities. The same squared deviation results in different tail probabilities if the numbers of observations in the 2 bins are not the same. After looking at some other plot, it appears that being young and having few axillary nodes increases the probability of survival for more than 5 years, whereas year of operation doesn't seem to matter. This is the same conclusion reached by Trevor Hastie and Robert Tibshirani when they analyzed this data set using generalized additive models. The data in our third example are observations on 680 earthquakes at Mount St. Helens. The variables are latitude, longitude, depth, date, and magnitude. I have spent quite a bit of time looking at those data, and there is a lot to be found. Here I will only show the part of the analysis that illustrates the use of odds plots. This is a plot of latitude on the screen x-axis, depth on the screen y-axis, and longitude on the screen z-axis. Notice that there is a separate cluster of relatively shallow quakes on the left, separated from the main bunch. Spinning the plot around the depth axis shows that most of the quakes are clustered in 2 chimneys that form an inverted V. To get a closer look at the bulk of the data, let's highlight all the fluff around it and then make a new data set containing only the downlighted observations, i.e. the core of the plot. Here are the statements that define a new dataset containing only the main cluster of quakes. Let's now draw a new scatterplot of depth versus longitude for the observations in the main cluster. This is the plot of the main cluster. The chimneys are clearly visible. Here we have added a histogram of the dates. We see that there were 3 major spurts of quakes. We can now paint the earthquakes in the first spurt and see where they fall in the scatter plot. Close scrutiny appears to show that the earthquakes in the first spurt tend to be in the left chimney and tend to be deeper. The effect, however, is by no means obvious and had gone unnoted in several inspections of the data. Drawing the odds plot immediately clarifies matters. The picture clearly reveals that the earthquakes in the first spurt are overrepresented among the deep ones and among the very shallow ones. Note that we can easily alternate between showing the point cloud, the odds, and both of them simultaneously. Let's switch back to the point cloud and paint the observations in the second spurt. Looking at the scatter plot itself does not give a striking picture, but the odds plot clearly reveals what is going on. The earthquakes in the second spurt tend to be on the right and of medium depth. However, there is a small area on the right where the quakes from the second spurt are neither over nor underrepresented. We now painted the third spurt. The odds plot clearly shows that its quakes are predominantly in the strange area that did not have any quakes in the second spurt. What have we learned? There are 3 spurts of earthquakes. Most of the earthquakes are concentrated in 2 chimneys reaching down into the earth. The quakes in the first spurt are predominantly deep down and fairly shallow, whereas the quakes in the second spurt are predominantly in the middle. The first and the second series of quakes left a small area untouched. Most of the quakes in the third spurt happened in this area. We have found out quite a bit about our data sets, doing nothing more sophisticated than simply looking at pictures. It appears that being able to look at multiple views of a data set simultaneously and to connect the views through painting significantly increases our ability to dissect and understand multivariate data. Odds plots seem like a promising idea. Looking at an odds plot, associations that might otherwise be overlooked hit the eye, and that is what good graphics is all about.